Hey guys, hope you're all doing good. In this video, we're going to be looking at classification using support vector machines. And this is one of those topics that when I was first learning it, I was searching all over YouTube and all over the internet, trying to piece together the different equations and how the equations should be implemented in Python correctly. And it was just a little bit of a mess. So what I'm hoping to do in this video is give a clear explanation of the math and how that directly translate into the Python code so that you don't have to go through that struggle that I went through when I was first piecing together support vector machines from scratch. And the first thing we'll be doing in this video is looking at hard margin support vector machines, mainly just looking at the math and intuition behind it. And once we have a good grasp of the math that's going on in support vector machines, we can expand out into the soft margin support vector machine, which that'll be applied to more real world problems with real world data. And this is where we're going to go into the math and intuition and implementation of the decision boundary, the loss function and its cost function, and then into gradient descent. Alright, so let's get started by taking a look at hard margin support vector machines. And just as a quick note, we're going to be using Jupyter Notebooks with NumPy, Matplotlib, and scikit-learn installed. So if you're wanting to follow along, make sure to set up an environment with all of these things installed. Okay, so to open with the hard margin SVM, let's go ahead and create some example data. Alright, so here's the data we're working with. We have the number of hours a student studied for their exam, the GPA of that student, and whether they passed or failed the exam in question. So looking at this first row, a student studied 5 hours, they had a GPA of 4, and they passed the exam. Whereas in the second row, that student studied 1 hour, they have a GPA of 2, and they failed the exam. Now if we mark the features and target with variables, we could say hours is equal to x1, GPA is x2, and the target is y. So given some x vector or array of numbers, we're trying to predict this final y value. And just for some extra notation, we can index each student with an I starting at 1. So the first student is at I1, second student is at I2, and the final student is at I equals m, and m is going to be the number of students. Then let's also index these features. So at j equals 1, we're looking at the first feature, and j equals 2, we're looking at the second feature. And if we had some more features, that would go all the way until j equals n, where n is the number of features. And just a little bit more notation that's going to be helpful for us later on is we're going to say x vector at I is going to be looking at the ith student's features. So if we said x vector at 1, that would be looking at 5, 4. And if, say, we wanted to get just the GPA of that student, we could say x at ij. So in our case, we're looking at x of 1, 2, and that will be the first student and the second feature, which is GPA of 4. And lastly, if we want to see if the ith student either passed or failed, we can use y at I. So if we wanted to see if the second student failed or passed, we can say y at 2 is equal to, well, that ith student is a fail, so that would be -1. Alright, but now that that notation is out of the way, let's go ahead and plot these points right here on a graph. Alright, so here we have the data pulled over. We have hours on the horizontal axis and GPA on the vertical axis. And then passing grades are marked in blue while failing grades are marked in red. So we have the passing up here and the failing down here. So given this data, we might want to try making predictions if a student would pass or fail their exam, given hours and GPA, by creating some decision boundary that cuts through all of our existing data. Now you might be thinking this decision boundary I drew is not a very good representation of if a student passed or failed, and that would be the right concern. Because if we look at the points closest to the decision boundary on either a passing or a failing grade, we'll notice that the X marker has a very small amount of space, while the blue marker has a large amount of space. So what we might want to do instead is erase this decision boundary and create one that has an even split between both the blue and the red points. So my drawing's a little bit off, but let's say this distance right here and this distance right here was the exact same. Then this might be a little bit better of a decision boundary. But again, intuitively, we could probably still make a better decision boundary. So let's try this one last time. All right, now this decision boundary would actually be our optimal one. And notice how this closest red marker right here has an equal distance as this blue marker. But another property of this decision boundary is that the space between the red marker and the middle and the blue marker in the middle is not only equal, but it's as long as it can be. And this concept is known as the margin. So here we now have this red line and this blue line, and notice how the red line is right at the border of the closest x value that's a failing grade, and the blue line is right at the edge of this passing grade. So what we can say about these two data points circled in orange is these are actually called the support vectors, which is a major part of the concept in the name support vector machine. But anyway, looking back at these red, yellow, and blue lines, they're really meaningless unless we have some equation to define them. And so what we can do next is actually write out those equations that represent these three lines. All right, so these three equations represent their corresponding colored lines. And we can see there's these W vectors and these bias values that we haven't looked at yet. And all we really need to know about these equations is the W vector and the B value is going to be the same in each of the equations. And it's going to be the parameters that we're finding by training the model using gradient descent. So to give some intuition, let's actually give these variables some values. So moving over to the left, we could say that weight vector is equal to, say, W1 and W2. Or maybe W1 is equal to 0.4 and W2 is 0.2. And then we'll set the bias value to negative 1.8. And again, these are the values that we're finding during gradient descent that allow us to find this decision boundary and these two ends of the margin. So if we had some completely other weight values, we might instead have a decision boundary that looks something way off like this, where this was actually W dot X plus B equals 0. But in our case, since we're just trying to build intuition, let's just use these values that make up these lines right here. And when I was first exploring support vector machines, I found it helpful to actually explore these equations and see how plugging in certain numbers resulted in finding points on our line. So let's go ahead and give an example of using this first blue equation. All right, and if we pick apart the equation, we'll have something like W1, W2, dot x1 x2 plus b is equal to 1. And to understand how this equation gets us to this line right here, let's see if we can replicate the result of that line by plugging in some x1 value, which again is the horizontal axis, and reach that x2 value, which is on that vertical axis, and see if we can get to this point right here. Or in other words, if we're looking at the table to the left, let's see if we can plug in 5 and get 4. All right, so now let's do some algebra to isolate this x2. So the dot product will give us this. And then we'll isolate this center term. And now we can divide both sides by W2. And let's clean this up a little bit. All right, so now let's plug in the bias, the weight values, and x1. All right, now if we solve this right side of the equation, we will end up getting 4. And that's exactly what we were hoping to get out of x2, which was up here in this first row, when we plugged in 5, which was our x1. And so instead, if we plugged in something like 6, we would get to this point right here. If we plugged in 4, we would get to something like this point right here. And if instead we use this yellow equation or this red equation, we would end up getting an equation over to the right that looks a little bit different. But hopefully that builds some intuition as to how these lines are actually being calculated. And with that finished, let's get back on track with the hard margin support vector machine. So as we were saying earlier, the objective is to find a decision boundary where this internal space right here is as large as it can be. And this distance right here we'll call the margin. And a couple things to mention about this margin is, first of all, it's going to be perpendicular to our decision boundary, and it's going to take on the form of this equation 2 over the magnitude of the weight vector. And so since we want to maximize this margin, we can start writing out the algorithm that lets us do that. And it might also be helpful to recognize what the magnitude of the weight vector actually looks like. So let's write that out. So in the case of this problem, we have w1 squared plus w2 squared. But if you're looking at a data set with a lot more features, you could go ahead and say this. So you'd end up adding the squared value of each w element and then square rooting the entire sum. Then this would give you the magnitude of the weight vector. But moving on, let's look at what the algorithm might look like for the hard margin support vector machine. Alright, so like we were looking at earlier, the objective is to maximize this margin value, which that's again represented with this distance right here. So we want to maximize the margin. Or in other words, we're trying to minimize that weight vector magnitude. And the parameters that we can update in order to minimize this weight vector, just like we looked at below, is the weight vector and the bias value. So we can update the weight vector and bias value. And another constraint of the hard margin support vector machine specifically is that any x point that's a passing grade, or in blue, should be above this wx plus b line equal to 1. Or in other words, any x value needs to be to this direction of the blue line. And if they lie on the other side, say right here, then this would cause a violation to the hard margin support vector machine. And this is actually where the hard margin name comes from, is that these support vectors, again marked in orange, must be touching this blue line without being past it, say over here. And the same would be true for these failing x points. So any x point that's on this side is good, but if it passes that lower end of the margin, then that would violate the hard margin SVM. So if we wanted to write that out mathematically, we could say this. So in this top blue line, if we pass in some x vector into wx plus b, then it has to be greater than or equal to 1 when the target value is 1. So at this point, we're looking at when this value is 1. And if we looked at a point to the right of that line, say this point, that would still be greater than 1. But if it was less than 1, say somewhere at this yellow point when it was equal to 0, then that would violate the constraint. And that would work the same way, but for -1 when y of I is equal to -1. And then we can also combine these two statements into a single statement, which looks like this. So here we're just saying if we had some arbitrary x, y, w, and b plugged into this left side, it must be greater than or equal to 1. Otherwise, our hard margin SVM constraints are violated. Alright, so that was about it for the hard margin SVM section. And next we'll look at the soft margin SVM, which works a little bit better with real world data, where you might have some anomalies, like say if you had a cluster of passing grades and a cluster of failing grades, but then every once in a while you had some anomaly score. Then with some data that looks like this, it's not possible to fit a hard margin SVM, because no matter where you set that decision boundary, you're going to be violating these constraints over to the right. So this anomaly issue is going to set us up for the soft margin SVM. Alright, and to start the soft margin SVM, let's go ahead and create a plot with just a bunch of passing and failing data points. Alright, so looking at this new data set, we're still looking at students and their hours and GPA to see if they either passed or failed an exam. And if we were to try to find some best fit line for this data, we might split it into something like this. And now let's add a margin to this yellow line. Alright, so a few things to note here is before we had this region as the passing region, or a unit value greater than or equal to 1, then this region had a unit value less than or equal to -1. And then this yellow region was in between -1 and 1. Or in other words, before we enforced that passing grades be in this blue region and failing grades be in this red region. But this constraint is not realistic given real data, because you'll often have anomalies, such as this red x point being way over near the blue points, and this blue point down here being around all of these red points or failing grades. So let's figure out a new constraint similar to the hard margin that will allow us to have some anomalies like these points. And again, we'll start with the hard margin constraint and then move on from there. Alright, so if we take a second look at this constraint right here, we're essentially ensuring that any blue points are at least 1 unit away from the center decision line, where this is a single unit right here. So anything at or past that point would pass the constraint. This would also be true for the red X points. So the hard margin constraint would say that anything that's at or past a unit of 1 toward that red line should be valid in that constraint, but anything less than that 1 unit, so anything on this section, should fail the constraint. So what the soft margin SVM does is it introduces a variable called slack. And to introduce this variable, let's look at an example point. So right now, this blue point is failing this constraint because it is less than a unit away from this decision boundary. So what we're going to do is take this distance between that blue X and that 1 unit distance toward the passing direction, and we'll define this distance with the slack variable. And now we can add that slack variable to our constraint. So now what we're saying is, instead of ensuring that our point lies at a distance greater than 1 unit, for the current example, we're instead ensuring that our point is within 1 minus our slack variable, which again, if this is our slack variable, then 1 minus that slack variable would result in this distance right here. Therefore, if we had a slack variable for each point that was on the wrong side of its margin border, then we can ensure that even if we have anomalies in our data set, this constraint can still be true. And since this slack variable is only needed for the points that are on the wrong side of their margin boundary, then we will be using the slack variable. Otherwise, we don't even need that slack variable. So these points don't need a slack variable because they're already in the right locations. So let's go ahead and write that out formally. All right, so now let's break apart these 2 new lines right here. So if this first condition is satisfied, where the point in question lies greater than or equal to 1 unit from that decision line, then we don't need a slack variable. On the other hand, if we're looking at this second line right here, we're saying if the point in question lies less than 1 unit away from the decision boundary, so for example, this would be less than 1 unit if we're looking at the blue point, then we will need this slack variable to offset our soft margin constraint. So we're going to need some slack variable equal to this distance right here so that we no longer are constrained to this border, but that border gets pushed down the distance of this slack variable to right here. Then that slack variable would be equal to 1 minus the point's distance from the decision boundary. All right, and if we are looking at the ith training example and we wanted to figure out what that slack variable is, either 0 or 1 minus that distance, then we can use this new equation. All right, so what this equation is saying is the slack variable at any given training example. So say we're considering either this point or this point, the slack should be equal to the max between 0 or 1 minus that distance from the decision boundary. So if the distance from the decision boundary in units is greater than 1, then we would have a max 0 of 1 minus something greater than 1, something like 2 maybe. Then this would result in a negative 1, and the maximum of that would be 0. So this point would need no slack. Now let's consider this point. So if we wanted to take the max of 0 and 1 minus whatever that distance is right here, which is obviously less than 1 because this would be considered our full 1 unit length. So this blue point might be at a unit distance of something like 0.2. The max of 0 and 1 minus 0.2 would be equal to 0.8. And that 0.8 also represent this distance right here. And that would be plugged in for the slack variable at that training example index. Okay, and with this new slack variable defined, we can go ahead and update our algorithm that tries to maximize this margin length while also introducing this slack variable. All right, so what we want to do in this algorithm is again minimize the magnitude of the weight vector, but now that we have the slack variable introduced, we're also going to want to minimize that. And so minimizing the magnitude of the weight vector was explained in hard margin SVM, and the reason we're trying to minimize this slack variable is so that we don't just have some large amount of slack wherever the program wants to have slack. The objective is still to minimize slack as much as possible and only use it where it's absolutely necessary. So that's why we want to minimize the magnitude of the weight vector and the slack. And if we want to formally write that out, all right, so all this is saying is we want to minimize the magnitude of the weight vector and the sum of all of the slack variables. And you'll notice we're actually squaring the weight vector, and that will allow gradient descent to work out better mathematically later. And then we're also adding this c constant right here. And this c is going to control how much of an impact the slack variable has on our minimization algorithm. Or in other words, if c was very large, then we would end up having a very large weight magnitude and a very low loss. On the other hand, if our c was very low, then we'd end up with a very low weight magnitude and a very high loss. Now you might be thinking, why don't we just use a really large c and that will result in a low loss? Well, the issue with that is that we might end up overfitting the model. So if we pick some good value for c that's not too high or too small, we'll end up with a good model that can generalize complex data well without overfitting to it. All right, and if we wanted to then expand out that slack variable, we could rewrite this algorithm one more way. And all we're doing here is taking this slack variable and expanding it out to this max function that we have up here. And another thing to mention is that this max function is also known as hinge loss. So this is a loss function that I mentioned in the introduction of the video, but this is actually what that hinge loss function looks like. And to give even more intuition as to what this hinge loss function is doing, let's go ahead and plot that next. All right, so this loss function can look a little bit complicated, but if you work it out, it's really not too bad. So the first thing we'll want to look at is this t term, which is represented by yi times the w vector dot the x vector plus b. And again, that result is going to signify how many units away from our decision boundary we are, which would go in this direction if we're looking at a blue point where y of I is equal to 1. Or a red point if y of I was equal to -1. So let's look at an example where y of I might be equal to a passing grade. All right, so if we were looking at a point, say around right here on the passing grades, then this might be 2 units away from that decision boundary. So this would be 1 unit and then 2 units away. So then that would make t equal to 1 because it's a passing grade times 2 because it's 2 units away from that decision boundary, which that would mean t is equal to 2. And then if we plug that into our loss function, then the loss for that point would be equal to the maximum of 0 and 1 minus 2. And since this is a negative value, our loss at that point would be equal to just 0. So if we plotted that on the graph, then again our t was equal to 2, so right here, and our loss was equal to 0. So that would be our point, t equal to 2, loss equal to 0. Now let's do the same thing, but for this red point right here. And we'll assume that this point is half of a unit away from the decision boundary, where this would be a full unit. So in this case, we would have t equal to -1 because the true value was -1, or a failing grade for y at I. And then given that wx plus b, that would give us a -0.5 value, so -0.5. And again, at -1, we're looking at this point of the red line. At +1, we're looking at this point on the blue line. And then 0 lies right on that decision boundary. But back to our problem. If we multiplied -1 and -0.5, the negatives would cancel, and that would leave us with +0.5. Now if you plug that into the loss function, then we'd get the maximum of 0 and 1 minus 0.5. So since 1 minus 0.5 is equal to +0.5, our loss would become 0.5. And if we plotted this on our graph, then t at 0.5, which is right here, would give us a loss of +0.5, which is right here. And if you were to find a bunch of t values depending on points that are on your graph, whether they're above that 1 unit boundary or under it, then it turns out you would get some loss function that looks something like this. All right, so now if you're online and you see the Hinge loss function somewhere and you're unsure what's happening, this is exactly what's happening. It's looking at the loss of any given point in your data set, where if that point needs some slack, then it's going to have some loss. And if that point doesn't need any slack, then the loss is going to be 0. All right, now back to our algorithm over here. We can go ahead and recognize this entire section as being our cost function. So given the current state of our soft margin support vector machine, we will get some cost value, and that cost value is what we're trying to minimize by updating the values of W and B. All right, so this might have been a lot to take in. If so, I would encourage you to take a step back and take in everything that we just went over. Otherwise, at this point, let's go ahead and jump into a Jupyter Notebook and start coding out our example data, come up with some weight and bias value, and then figure out the cost of our support vector machine. All right, so now we're back in the Jupyter Notebook. Let's go ahead and initialize some training data and then make some predictions on that data using a weight and bias. And then we'll create the cost function and test that against our model. So here we can initialize some x, y, weight and bias. Alright, so here we have an x and a y initialized using this makeBlobs function. And in here we're going to have 100 training examples with 2 classes and a standard deviation of 3.5 to add some random noise to our data. And if you'd like to follow along, then you can use this random state of 42. So let's take a look at our data. Again, we have 100 training examples with 2 features, where this first array represents our x inputs, and then that second array represents what those outputs look like. And looking back at the type of data we're working with a support vector machine, a passing grade will be represented by a 1 and a failing grade will be a -1. So we'll actually want to change these zeros to a -1 and keep this 1 as a +1. Alright, so in this code block, we're essentially just converting all zeros into -1s. And for consistency with data types, we're going to add this floating point just so that we can be working with floats in the y and floats in the x. So now let's create a weight and bias value. Alright, so for our weight value, we have 2 elements, just like how we have 2 features in our x input. And then our bias is a single floating point value. And now if we wanted to make predictions, we're essentially saying anything that's to the right of this decision boundary should be a passing grade, while everything to the left of it should be a failing grade. And if we look back here at these 3 equations, plugging x into our wx plus b function should result in a 0 at this decision boundary, and a positive value to the right of that decision boundary, and a negative value to the left of that decision boundary. Or in context of our problem, anything above this yellow line should be a passing grade, and anything under it should be a failing grade. So let's write that out in code. Alright, so what we currently have in this prediction function is we're passing in x, w, and b. We're initializing m, which is the number of training examples, which in our case was 100. And then we're creating an empty array for all of the y predictions. And then in this for loop, we're going to look at each training example and figure out what its y prediction should be. And to do that, we're going to apply the dot product w dot x at I plus b. So that's just like what we saw up here, w dot x plus b. And if that results in a positive value, that would be a positive prediction. And if it results in a negative value, that would be a negative prediction, such as passing or failing an exam. And so what we can do is get the sign value of each y prediction, whether it's positive or negative, and just store it as a +1 or a -1 in y preds. And then return that y preds. So let's see what that might look like in code. Alright, so if we pass in the first 10 x values along with our weight and bias value, then we're predicting that each of those examples should result in a positive y value. And that's going to be incorrect because we saw earlier that the first 10 elements of our y array are -1s and +1s, not just all positive ones. And to better grasp what these predictions look like, let's plot them on a graph. Alright, so far in this function, we're plotting two plots. The first one is going to show off the y true values, and the second one's going to show off what the predictions look like. And we can add the decision boundary in a second, but let's see what this looks like so far. Alright, so it looks like in these two plots we have some purple and yellow points, and these would represent the two output classes, that being +1 and -1, determined by the x input features. And now we'll add the decision boundary with a margin to see a little better what's going on in this y preds plot. Alright, so here we have these x values and y values. The x values are just going to be the lower and upper x limit, so that would be this lower x limit here and this upper x limit right here. And then we're plugging those x values into these three lines. And those three lines are going to correspond to these functions right here. More specifically, this blue equation right here, where we plugged in an x value and figured out what the y value was, is going to correspond to this bottom equation with yyp. Notice we have 1 minus b minus w1x1 divided by w2. That's going to be the exact same thing that we see right here. And if we wanted to update this function to fit for this -1 margin, then we could just add a -1 right here as shown in this -1 unit. And that will give us points along this line down here. Whereas if we wanted to find points right along that decision boundary, we would be using this equation, which if we isolated x2, then this 1 would become a 0, as shown in this right side of the equation. So in that negative case, we would tack on that -1 to the right side of the equation. And in that middle case, which is our decision boundary, we would just have a 0 in place of that right side of the equation. So this will give us the decision boundary line and that lower and upper margin. So now let's plot those onto our y preds. And it looks like at some point I accidentally removed this +b, which is necessary in the prediction function. So I'll make an edit to that earlier in the video, but let's go ahead and run this now. And as we can see, we have this clear decision boundary cutting through our data, where the +1 values, signified by this blue dotted line, represent the +1, or in our context earlier, the passing grades. Whereas everything on the bottom, near this red dotted line, is going to mark the failing grades, or the -1 case. And looking at both of these graphs, we can see that there's a lot of inconsistency between y true and y preds. So let's go ahead and calculate the loss for each training data point using the Hinge loss function, and then we can plug that into our cost function to get the cost of our overall model given some weight and bias value. Alright, so here we have our function for calculating hinge loss at some x and y. So let's refer back to this graph that we looked at earlier. We're first calculating that y prediction using this wx plus b, and then multiplying it by the sign of that true y value, which is either +1 or -1. And then once we plug that t value into our max function, we're then able to see if our prediction is on the correct side of our margin. And if it is, then there should be no loss. But if it's on the wrong side of that margin, then there should be some loss, and the magnitude of that loss should correlate directly with how far away our prediction is from the upper or lower end of the margin, depending on if that point's y true was a -1 or +1 value. And what we're going to do next is plot out this loss function so we can see exactly what that plot looks like in Matplotlib. Alright, so let's take a look at this code and see how it gets us to this plot. So first we're calculating this t value for each xy input, and that's exactly what we were doing with this t down here, or in these t examples we looked at in blue and red, and that will mark our x-axis for each point, and then our y-axis is marked with the loss array, and then again the loss array is equal to the maximum of 0 and 1 minus t, which we looked at in orange. And if we plot this t against this loss, we'll get a plot that looks something like this. And it might be kind of hard to see, but this t equals 1 is our critical point where we go from having a loss to having a 0 loss. So it looks like our loss function is working, and now we can incorporate this into our cost function. So let's go ahead and do that. Alright, so in this cost function, we're passing in x, y, weight and bias, and then c, which is our regularization term. And in this function, we're going to iterate over all m training examples. In the first step, we're calculating the cost for our margin, and that's going to be using this 1/2 times the magnitude of our w vector squared, which that can be represented in this first line right here. So if we wanted to get the magnitude of our w vector squared, that would be in this parentheses right here. And then we want to multiply it by 1/2 or divide it by 2. And next we want to get the sum of all of our hinge losses and then multiply it by c. So we can initialize our hinge loss at 0 and then iterate over each training example, calculate the loss at that index, and then add it to our total hinge loss. And then finally multiply that sum by c. And then once we have the margin cost and our hinge cost, we can add those together into our total cost and return that. So let's actually go ahead and see what our cost looks like right now. And we get a value of just over 442. Now what we want is to minimize this cost by updating our weight and bias values to better fit the data. And when our decision boundary and margin is better fit to the data, we'll end up having a lower cost. Now to achieve that, we want to apply gradient descent. So let's go back to the whiteboard and take a look at what the gradient descent step looks like. And very quickly, I'll go over some intuition with what gradient descent is going to look like for our model. And to do so, let's assume that every element in our weight vector is some constant value except for our first weight element, and our bias is also some constant value. And this later on would hint to the partial derivative of j with respect to w1. But what we saw a minute ago is we have some weight value, say at this point here, that gives us a relatively high cost value. And let's say we updated that weight value to some different lower value, then maybe that would give us a lower cost, meaning that weight value would cause our decision boundary to better fit our data. And then let's say we changed w1 to some even lower value, and that resulted in a much higher cost. Then if we tried every possible value for w1, then that would change our decision line in either a good way or a bad way, leading to a good cost or a bad cost value. So testing out every possible weight value might end up with a curve in the cost function that looks something like this. Then we can say when we have a weight value that's just right, we'll have a minimum cost. But if we had a weight value that was too high or too low, our decision boundary would be way off in predicting what our y true values are. So that would result in a very high cost up here or down here. So what we can do in this case is if we initialized our weight value to some value that's way too high, and that resulted in a very high cost, then by taking the tangent line or the slope at jw1, we would get a tangent line that looks something like this, or in other words, we would have an increasing slope. And in another example, if our cost was very high, but our w was low, then we might have a slope that looks something like this, which is a negative slope. Then we can see when our weight value is too high, that results in a positive slope in our cost function, so we might want to decrease w, and that will result in our decision boundary fitting better to our data. Whereas if our slope was negative on that j of w1, then we might want to increase our w, and that would also give us a better decision boundary. So at this point we can see that if we can figure out what slope we get in our cost function for j of w1, then we can directly determine if we need to increase or decrease our w1 value. So a positive slope would mean decrease w, and a negative slope would mean we need to increase w. And if we wanted to combine these two into a single line, we could say we want to set w equal to itself minus the slope. So again, if this slope was positive, then we want to decrease w. And if this slope is negative, then we want to increase w. And we also want to ensure that any changes to w1 is not going to be too drastic of a change. So let's say we're looking at the slope of jw1 at this point right here. Then we can clearly see we want to increase w1 to get a better decision boundary line. So if we were to say increase it too much, then we might end up with an even worse cost than we had initially. So to fix that, we'll add this alpha value, and that will be our learning rate. which is essentially just some very small value that ensures that any step toward that global minimum is going to be small. And then as we approach that global minimum, our magnitude of slope is going to decrease. So this value right here is going to decrease as we get closer to the global minimum of the slope in the cost function. So that will naturally cause us to make smaller and smaller steps until we reach that global minimum. And mathematically, this slope is going to be written as the partial derivative of j with respect to w. And in our graph example, we're looking at w1, but this would apply for any w index. So we can just say wj. And this same algorithm could be applied to our bias value. So if we consider this w vector to be some constant value, then our cost function is either going to increase or decrease depending on how good our bias value is as well. And in that case, we're also going to want to update our bias value. And since we're looking at the slope given b, we're then going to want to use the partial derivative of j with respect to b instead of with respect to w. So let's go ahead and rewrite that gradient descent step in our algorithm section. So in this algorithm, we're going to repeat the following steps. We're going to calculate the partial derivative of j with respect to wj for each j starting at 1 going all the way to n. And then we're going to update that j weight element, setting it to itself minus alpha times the slope or partial derivative of j with respect to wj. And then we're also going to update our bias value, setting it to itself minus alpha times the partial derivative of j with respect to b. And if we can successfully carry out this step right here, then this will effectively make our decision boundary best fit our data while optimizing both our margin width and the amount of slack that we're using, shown in this hinge loss function, with that regularization parameter c to determine how much hinge loss should have an impact on our cost function. So this is almost complete for us to start applying gradient descent. And our last step is we just need to figure out what these two terms look like. All right, so first let's look at the partial derivative of j with respect to wj. All right, so in order to take this partial derivative with respect to wj, we're going to need to apply the partial derivative to the cost function shown in these brackets. Now let's see what the solution looks like once we actually apply that partial derivative. All right, so once we calculate the partial derivative with respect to wj, we'll get wj minus our regularization parameter times the sum of this piecewise function. So in this sum, we're looking at each training example and its loss. If the loss of that training example is equal to 0, then we're going to return 0 in the sum. Otherwise, we'll return y at I times x at ij. And that's all we need to do for the partial derivative with respect to wj. Now let's look at the partial derivative with respect to b. Alright, so here we have something a little bit different. In the partial derivative with respect to b, we're not going to have this wj because this entire first term in the cost function can be seen as a constant and it doesn't have any bias in it. So no coefficient's going to be pulled out during the derivative. And then we're still going to have that minus c times the sum, where if there was no loss, then we don't need to add any value, so we'll say 0. However, if there was a loss, then we're going to add y at I. And again, the reason we're adding just y at I without any x variable attached to it is because in our cost function, we're looking at y at I, and that gets distributed to b. So the only coefficient during the derivative is going to be y at I. Whereas if we looked at this top equation, our partial derivative is going to give us y at I times x at ij, because in our cost function, y at I is being distributed to this whole term right here. And since we're taking the partial derivative with respect to wj, y at I and x at ij would become the coefficients that get pulled out during our derivative. All right, now that we have these partial derivatives calculated, let's plug them in to our algorithm and see what the final algorithm looks like all worked out. All right, so here we have our updated algorithm. We're updating each wj and b. For wj, we're updating it by a negative alpha times everything we saw in these brackets right here. One small change to the top and bottom equations is we now have this 1. And basically what that's saying is if this inside of these parentheses results as a true, meaning if this loss section is greater than 0, then we want to return a 1 for this whole section. Otherwise, we'll return a 0. And then we'll multiply that 1 or 0 by yi xij. And this whole right side portion is going to be contained within our sum. And then taking a look at the bias, we're setting it equal to b minus alpha times this whole inside of the brackets like we saw above again, except now we're just multiplying against that yi inside of the sum. And one final change we can make to this to clean it up a bit is apply vectorization to these wj changes. So we can actually apply all of these wj changes in one go using vectorization, which is supported by NumPy. So if we went ahead and used the vectors instead of each j value, then our final gradient descent algorithm would look like this. And with that done, we can go back into Jupyter Notebooks and code it out. All right, and the first step we're going to take is calculate just the gradient, which is all of the partial derivatives. And then we'll test out that gradient to make sure it's actually lowering our cost function. And if that's successful, then we can write out our gradient descent algorithm, which is going to apply a bunch of gradient descent steps. So first, let's write a function that calculates our gradient. All right, so here's our calc gradient function. We're initializing n for the number of features we have and m for the number of training examples we have. djdw and djdb are going to be initialized with all the 0 values. And then for each training example, we're going to calculate what that hinge loss value should be. And if it's greater than 0, then we're going to proceed using this first if statement. Otherwise, we're going to use this else statement right here. All right, so going back to our whiteboard, let's look at this section for our w vector. If our loss is greater than 0, then we're going to want to use this yi xi. So that will be this first line, and if the hinge condition is true. But if our loss is less than or equal to 0, then this is going to result to be 0, and we're going to ignore this yi xi. So at that point, we're only adding the w vector, and that's shown in if hinge condition is false. Now considering the partial derivative with respect to b, if we did have a loss, then we want to use this yi value, so that's shown right here. However, if there was no loss and this part resulted to a 0, we would ignore this yi. And since there's no w vector here, this whole portion would just result to being a 0. Or in other words, if our hinge condition was false, we would add nothing to djdb. So let's go ahead and run this and return our current djdw and djdb. All right, so our partial derivatives for our weight vector are shown in this 2-element array. And the partial derivative for our bias is right here, the single 44 element. And now that we have the partial derivatives shown in these brackets in the top and the bottom, let's apply some learning rate and update our weight vector and bias value and see if we can reduce our cost score. All right, so here we just applied a single step of gradient descent, and that dropped our cost by over half. So it looks like our calculate gradient function worked pretty well. And since we have a function to plot our y true versus y pred, let's go ahead and do that one more time before moving on to the gradient descent function, just to see how that single gradient step affected our decision boundary. All right, so our decision boundary and margins are still not great, but it looks like we're correctly classifying points a little better than we were earlier. So maybe if we apply gradient descent with multiple iterations, we can get a line that almost perfectly fits our data. So let's go ahead and write that function now. All right, so in this gradient descent function, we're passing in x, y, and our current weight and bias values. And then we'll go over 1,000 iterations of gradient descent with our C regularization parameter set to 1 and our alpha set to 0.001, just like we had up here. And then history step is going to be 100, and that's just going to record our cost every 100 iterations. So looking into this function, our history is going to initialize as an empty dictionary, and then in each iteration, we're going to calculate the current gradient and then apply it to our weight and bias values. And then we're going to calculate the cost and add it to our history every 100 iterations. And finally, we can return the history and the updated weight and bias values. So now let's run this gradient descent algorithm with our x, y, weight, and bias and see if we can get a little better results than we did with just a single gradient descent step. Alright, so previously our cost went down to 182, but after running gradient descent over 1,000 iterations, we got our cost all the way down to 18, which that sounds a lot better, but let's go ahead and plot that to see how well our model's actually doing now. And in these two plots, you can almost hardly tell which one is the y true and which one is the y pred. So it looks like our model did pretty well training these weight and bias values. There might be a few incorrect predictions, but that would make sense because there's a little bit of overlap between these yellow and purple dots. Now let's go ahead and see what this history value looks like in a plot so we can see how our cost decreased over the iterations. Okay, so if you couldn't tell in these numbers right here, this is what our cost looks like over the iterations. It started off pretty high and then immediately dropped off. And it looks like it found that global minimum cost almost immediately. Alright, so that's about it for support vector machines and making classification predictions using the hinge loss function. If you're looking for where to move on, specifically within support vector machines, I would recommend taking a look at kernels. That's actually an area that I'm trying to study right now as well, so feel free to link any sources to support vector machine kernels. Otherwise, thanks for watching. I hope you learned a little bit about support vector machines in this video, and if you want to see more videos like this, make sure to like and subscribe. Thanks again, and I'll see you in the next video.